Let's continue. So we need to prove the second part of the Bochner theorem, which is a real non-trivial part. But before, we need some remarks about positive definite functions. So I remind you that a function phi on a group G is said to be positive definite if we have the following inequality. So a function is positive definite if we have the following system of inequalities, and we must prove that if such a function is continuous, then it is representable by the inverse Fourier transform of some measure. Okay, and before going further, we need some properties of such functions, and first, let's take n equal to 1 here. So x, s are some points of the group G. So when n is equal to 1, then there is only one term here, and this difference is 0. So we obtain C bar phi of 0 is non-negative, and C is arbitrary, so simply phi of 0 is non-negative. Okay. So this is the first property. Then take n equal to 2. What do we have? C1 absolute value squared phi of 0 plus C2 absolute value squared phi of 0 plus C1 C2 bar phi of x1 minus x2 plus C1 bar C2 phi of x2 minus x1 is non-negative. Okay? So we have this. Now we take C1 equal to 1. This is homogeneous in the collection of coefficients C1, C2, so we may normalize it taking C1 equal to 1. And for C2, I'll write simply C. So what do we obtain? We obtain phi of 0 plus C squared phi of 0 plus C bar phi. And also let's take x1 equal to 0, and we write simply x for x2. So this will be minus x. Where by is here, yes, plus C phi of x. Okay, and this is non-negative. this non-negative, but now we only, at this point, we only need to know that this thing is real. Because about this thing we know that it is real, because phi of 0 is non-negative, so this one is real. This one is real, and this means, first take C equal to 1, then we see that this sum is real, and this means that phi of x is equal to alpha plus I beta, and phi of minus x is equal to alpha minus I beta for some alpha and beta. So alpha 1 and it's alpha 2. So the sum is real, so they have opposite imaginary parts, so we have this. And now we take C equal to I, and this implies that I phi of minus x plus I phi of x is also real. And when we look here, we see that alpha 1 must be equal to minus alpha 2. So the second property is that phi of minus x is equal to minus phi of x. Yes? Okay, Meyer is here. Meyer is here. Probably everything except this inequality, because I'm going to use it once again. I'm going to use it once again. So I need this inequality. Not minus alpha 2. Not minus alpha 2, but what alpha plus beta. So with complex conjugation maybe. So here it is correct, and when we multiply by I, so this must be okay. Okay.
Minus I.
Yes. Alpha 1 plus alpha 2 is equal to 0. Yes. Okay. Alpha 1. So alpha 1, alpha 2 equal. No.
Because you lose a minus in front of I.
Minus here, minus, yes? Here minus. Minus here. Okay. So minus here. So we have this. Yes? We have this. Okay. And now let's look at this quantity. These two guys are complex conjugate. So here we have, in fact, let me use the eraser. Here we have, in fact, the real part of C phi of x. Yes? And so this is greater than or equal to 0. And now for C we take this time an arbitrary complex number. C equal to T e to the power I theta, where T is a real. So what do we obtain? T squared phi of 0 plus t, the real part of e to the power I theta phi of x plus phi of 0. It is non-negative. So if this is a quadratic polynomial, then we see that the discriminant must be non-positive. And the discriminant, I forgot the number 2 here. Number 2. And the discriminant divided by 4 is, for this theta, I can choose it so that this guy is equal to the absolute value of phi of x, of course. So let's choose it in this way, and then we obtain the following thing. Well, and this means that we have this inequality, but this is only in the case where f of 0 is not 0. But if f of 0 is 0, then phi is identically equal to 0, because then this linear function cannot be sign preserving unless this coefficient is equal to 0. Okay. So in any case, we have this inequality, and it follows that this function phi is bounded. In any case, it is bounded, and phi of 0 is the greatest value. And the last thing to prove in the following inequality, let me write it out first. May I erase this? So the third property is that here I must put the real part. Oh, like this. From this it follows that if phi is continuous at 0, then it is uniformly continuous. Yes? Okay, in any case, we may assume here that phi of 0 is not equal to 0 without loss of generality, because otherwise the function is 0 and there is nothing to prove. So we assume that, and to prove this inequality, we write this inequality but with n equal to 3. N equal to 3. So all this, in fact, I remember this by heart, but it is easier to use some external memory. Well, 1 is equal to 3, so we obtain the following. These are diagonal terms here, and what else? Will be C1, C2, phi of x. There are 3 points, and one of them we take x1 equal to 0, and for x2 we use the notation x, and for x3 the notation y. Let it be this way. Then here it will be 0 because of this, and here we obtain phi of x bar because it will be phi of minus x plus c1 c3 bar phi of y bar plus c3 bar phi of x minus y plus another 3 terms, c2 c1 bar phi of x plus c3 c1 bar phi of y plus here c2 c3 c2 bar phi of x minus y bar. Okay, so the terms which are one lower than another, they are complex conjugate. Okay.
So shouldn't it be minus for minus equals C2?
Sorry?
Shouldn't it be minus?
Yes, it should be, but we know already this thing.
Yes, but there is minus. There is minus.
There is minus. Okay. Somewhere there is minus. Probably there is no minus here. Well, what we obtained? So we had alpha 1 plus e beta and alpha 2 minus e beta, and then what's about alpha 1 and alpha 2? So minus alpha 1 plus alpha 2 is equal to 0. So they're equal simply. So okay, no minus. No minus because we had this was phi of x, this was phi of minus x, and then we put I instead of c, that inequality which disappeared already, and so this times minus I, and this plus this times I should be real. So we have this. Okay, no minus. Sorry. So anyway, I realize this in terms of real part of something, yes, because these two lines are complex conjugate to one another, and also I put at once C1 equal to 1. This is again normalization because everything is homogeneous, and C2 for C2 and C3 I take something opposite like this. What do we have to, well, maybe let me rewrite this before taking this values for our constants. So when I put the real part, in principle, I can put bar of each term if I want. So, well, okay, and then I choose these values of the constants. So we obtain 1 plus.
Risk lab 0 to the first term.
F0. Yes, I forgot it. So 1 plus 2 absolute value of c squared phi of 0 plus 2 real parts of c phi of x minus c phi of y. Well, I did remove this bar after putting c1 equal to 1 because it is the same. Minus c squared, so here it is the absolute value of c squared phi of x minus y. Okay, and again we take for c something like t e to the power e theta, where this theta is taken in such a way that e to the power e theta phi of x minus phi of y is equal to the absolute value of phi of x minus phi of y. So let's write this as a quadratic polynomial. So what do we obtain? So t squared will come from here and from here. So 2t squared phi of 0 minus the real part of phi of x minus y plus 2t the absolute value of phi of x minus phi of y. So this is by the choice of theta. This comes from here, and also it remains another term, phi of 0, and this is non-negative, and we have assumed that phi of 0, well, we have assumed so this is non-negative, so in principle, well, the discriminant is non-positive, and the discriminant, this tells us that phi of x minus phi of y squared doesn't exceed to the real part, and here this is real, so I can write this real part of this difference, the real part of phi of 0 minus phi of x minus y, like this. Well, the only tiny question is what happens when this coefficient is 0. Then this is not a quadratic polynomial, but if this coefficient is 0, then this is a linear function, and it can be non-negative for only if this difference is 0, and then there is nothing to prove here. Okay. Now, in principle, even I don't need all of that. Well, what is essential here? It is essential that phi is bounded. This property, so probably this property 4, and there was also the property 3, that phi of x is dominated by phi of 0. So this was also proved. Well, I need this thing, I need this thing, and these two inequalities are relatively easy. They require only two terms in this basic inequality. This is more complicated, but this is somehow a toy, because if I assume from the very beginning that my function is uniformly continuous, then everything goes smoothly. Well, yes?
It seems that there is phi of 0
Minus where?
on the right side.
Ah, yes. I forgot that, and it is present here. So
Really square in the
square. No. Yes, it is square. Yes, it should be square here, and phi of 0 here. Okay. Now it is. Everything is correct. Mm-hmm. Well, in any case, this tells us that if phi is continuous, then it is uniformly continuous, but this uniform continuity is not very much important. So if I only assume that phi is continuous, I can argue as I shall argue now. At the end, we see that phi is uniformly continuous in any case because we find a representation of it in terms of a measure. So it is the inverse Fourier transform of some measure, and all such functions are uniformly continuous. So anyway, we have proved these properties, and now we want to prove. We turn to the difficult part of the Bochner theorem. So the statement is that if phi is continuous and positive definite, then there is a negative measure mu of the group gamma such that phi of x is equal to the integral of a little gamma of x d mu of gamma. Okay. So what is called the inverse Fourier transform of the measure mu inverse, because there is no bar here. Okay. And now the first thing to do, we want to rephrase this basic inequality, and the rephrasement is as follows. Well, from this inequality, so claim, it follows that for every f in L1 of G, we have the following. Okay, so this is a direct consequence of this inequality. Why so?
Maybe we lose a bar in.
Sorry?
We lose a conjugation f y bar.
F.
Because ck we have a bar, so here should have a bar.
I don't understand.
Fy.
Fy.
These should be conjugation.
Yes. It should be conjugate. Sure. Thank you. Thank you. Should be conjugate. Well, why so? First, note that we may assume that our function f is continuous and compactly supported, because functions of this sort are denser than one. So if you prove this for every continuous compactly supported function, then by a limit passage, by approximation, we can prove this. And after that, after we assume that f is continuous and compactly supported, it is easy to reduce such an integral to such a sum, not quite reduce, but to approximate it by such a sum. Simply, we take the compact support k of f, then we split this k into disjoint portions, so that on each portion the oscillation of f is very small. F is uniformly continuous, so it is possible to do so. And also we may assume that the oscillation of phi, of phi on each such portion is very small. That is, I can write that this is approximately, this integral, so the integral over g, f of x, f bar of x, j, phi of x minus y is dx dy is approximately equal to, so we replace on each portion, in fact this is over k cross k. K is split into portions where everything doesn't differ from all values of f doesn't differ from some value very much, and so we just replace f with the value at this point. We do a very small error, so it is approximately equal to the sum of j and k. This is a finite sum, and there will be f of x j, f bar of y, okay, xk, say, phi of xj minus xk, and there will be also the measures, the Haar measures of these portions. So when we replace this function by all functions by values at something appropriate, then we obtain this sum, and this sum is non-negative because of this. So we simply unite this with this, and okay. And also I forgot to say that we may assume that phi of 0 is equal to 1 just by normalization, because if phi of 0 is equal to 0, then there is nothing to prove. Our function is identically 0, and the 0 measure is represented. And otherwise, we can divide everything by phi of 0. We can assume this, and then phi of x is less than or equal to 1 everywhere. So, okay. Now we need a measure on the group gamma, and how do we obtain a measure in general? What we do to obtain a measure? We use the reciprocation theorem. So we need to produce some functional on the space of continuous functions on gamma that tend to 0 at infinity. So this functional should be positive, and when we have this functional, we obtain a measure, and okay, so we need a functional. But we need to obtain this functional from this inequality, and what here is difficult is the thing that this is on G, and we need some estimate in terms of the norm of something on gamma, because we need a measure on gamma. So how to pass from G to gamma here? So I remind you some general fact which I already recalled. This is a fact from the Gelfand theory, and it is related to an arbitrary commutative Banach algebra, so let A be a commutative Banach algebra. So let M of A be its spectrum. The Gelfand space. Then if we take an element X in A, then its spectral norm is equal to the limit when k tends to infinity of the following thing: the kth root of the norm of x to the power k. What is called the spectral radius of the element x. So the spectral norm is equal to the spectral radius, and here there is again some difference between algebras that have unity and that have no unity. If our algebra has unity, then the spectral radius is simply the radius of the smallest disk centered at 0 that contains the spectrum of the element X, and then this directly follows from Gelfand's arguments. If there is no unity, then the notion of the spectrum is somewhat ambiguous because you have no invertibility then. I mean that if we adjoin a unity, then this will be the genuine spectral radius, but we even don't need this because we only need this formula. We not need to know that this is the spectral radius. We only need to know that this limit is equal to the spectral norm. And so, okay.
What is X hat?
X hat is a Gelfand transform. I mean that, for every element of A generates a function on the maximal ideal space. So every point of this space is a multiplicative linear functional. So x hat of t is t of x simply. So x hat is a function, is x treated as a function on, yes. So, and in our case, this is precisely the Fourier transform. Okay. Now we have this inequality for every function in L1. So let's define some functional t phi of f. This will be simply the integral over g f of x p of x dx, and this is for f in L1 of g. So this is a continuous linear functional on L1, because here we have a bounded function, bounded and continuous, and moreover the norm of this functional as a functional on L1 is equal to 1, because this norm is equal to the essential supremum of this phi, modulus of this phi, and this phi is dominated by 1 in modulus, and also it is equal to 1 at 0, and it follows that the essential supremum is also equal to 1 because it's continuous. So okay. Here is a functional, and we should prove something for it, some estimate for it in terms of the spectral norm, in terms of this guy. So let's introduce the following notation. We already used this function when we studied Fourier transform, and we used it to prove that the algebra of Fourier transforms is self-adjoint, if you remember. But now it will be also useful, and so consider the following sesquilinear form. So what happens here? This form is linear with respect to the first argument and anti-linear with respect to the second argument because of this bar here, yes? And also it is symmetric. It is symmetric if I interchange f and g, then I obtain the same, and moreover, we can even prove some formula which will involve this inequality. Let's write the definition of the convolution. So this quantity is equal to the integral over g of phi of x, the integral over g of f of u, g tilde of x minus u, du dx. Well, we change the order of integration and we use the definition of this function g tilde. So it is equal to the integral over g, of phi of x, g u minus x bar dx f of u du, and then we change a variable to arrive at the following. So it will be equal to, after a change of variables here, it will be equal to the integral over g f of u g bar of y phi of x minus y. So this new variable y is u minus x. Phi of u minus y. Of u minus y. Seems to me, yes. U minus y, okay. And this is non-negative by this inequality. Non-negative if f is equal to g. First, we see from here that this is symmetric. This is symmetric. That is, well, I was wrong when I told that it's symmetric. I mean that if we interchange the order of this argument, then we obtain the same, but with bar overhead. And from here it is seen that it is so. And when f is equal to g, this is non-negative. So this is sesquilinear form satisfying all properties of a scalar product, except non-degeneracy maybe. So we may write the Cauchy inequality for this form. Yes? Well, so we have following thing. Okay. And this is true for every f and g in L1. And now, from this I deduce some inequality involving only one function f. For this we some approximate identity. For this function g, I mean that we shall put here many function g which form some approximate identity. Okay, so simply let V be asymmetric compact neighborhood of 0. And let g be equal to the characteristic function of this neighborhood divided by the Haar measure of this neighborhood. I shall denote Haar measure in this way. Okay, so this is a function normalized in L1, and when V shrinks, this forms an approximate identity. What else? Since V is symmetric and G is real valued, we see that for this function, G tilde is equal to G simply. The neighborhood is symmetric, the function G is real valued, so it is invariant under this tilde, a Hermitian element. And when we put this, okay, So here on the right, it will be on the left, sorry. On the left, it will be fg is equal to the integral over g, the integral over v, f of x, 1 over the measure of v, phi of x minus y dy dx, and I remind you that t phi of f is equal to the integral over g of f of x phi of x dx. I claim that these two quantities are very close to each other when this neighborhood is small, because this function is uniformly continuous. So if v is small, then this is very close to phi of x. And the entire integral is in y is very close to phi of x. Okay? So in principle, taking for g such elements, we can make this quantity as close to this one as we wish. And after that, what do we have here? Here we have something very close to 1, because what is that? This is simply 1 over the measure of v squared, integral over v, phi of x minus y minus 1 dx dy, and when x and y run through some small neighborhood of 0, then this is very close to 1, because I remind you that this is precisely the value of phi at 0. Okay? So this thing is close to 1, and it follows that after putting here an approximate identity, we obtain the following inequality. So from this, we obtain something related to only one function f. Okay, by approximation, yes? So this is close to 1, this is close to t phi of f, so we obtain this inequality, and what is that?
It's not modulo squared, it's v squared and then modulo.
Well, but that is the same, this number. T phi of f, this is number. Complex, yes, but.
It's just a number.
Complex, really complex. Okay. Well, and what is that? What is that? I remind you that this is okay. This is t phi of f convolved with f tilde. So we have this inequality. But now consider this function h equal to this convolution. Let h be f convolved with f tilde. Well, first I claim that if I take tilde of h, then I obtain h. well, now what should I do when I put tilde here? I should replace x by minus x, so there will be plus here, and I should put bar over everything. So bar will come here, and here there will be no bar, and after that I simply declare this u plus x a new variable, and after change of variables I obtain this, right? So again, this is a Hermitian element. This tilde is a sort of an evolution. Okay, so let me arrange this, and now we continue. So T phi of something is estimated by this thing. So let's apply the same inequality to this term. This is T phi of h, and this is less than or equal to T phi of h squared to the power 1/2. Here I mean square in terms of convolution. So square is convolution square. It is convolution of h with itself. In fact, I should write here the convolution of h with h tilde, but h tilde is the same as h, so I can write this thing, and I can continue. And also here it is already non-negative, because of this basic inequality which I erased which follows from positive definiteness of phi. So I can continue. This is less than or equal to T phi of h to the power 2 squared 1 over 2 squared, and so on. Okay. T phi. And now I use the fact that the norm of T phi doesn't exceed 1. It is equal to 1 simply. So this is less than or equal to the norm of h to the power 2 to the power n, and all of this to the power 1 over 2 to the power n. So again, this is the convolution power. This is n1 of g. And we know that this tends to the spectral norm of the function f. So the resulting inequality is that T phi of h. I put the modulus here, but I could avoid this because this is positive. T of h is less than or equal to the norm of the Fourier transform of h in L infinity of gamma. Okay. Yes. And we also have this inequality, and it follows that well, and what is this? What is this? Okay, let's calculate. So h hat, what is that? This is f hat times f tilde hat. Yes? Because it's convolution and our Gelfand transformation is multiplicative. Now we already calculated that f tilde hat is equal to f hat bar. Yes? So this is f hat bar. So we already made this calculation, but if you don't remember, this is very, very, very easy. Well, this is just you write, and so this is f hat absolute value squared. And we have this inequality. Then we see that this is equal to the norm of f hat in L infinity of gamma squared. Okay? And this dominates this thing. So finally we obtain the following, that T phi of f is dominated by the norm of f hat in L infinity of gamma squared. This is precisely not squared, without any square. So here we have a square. Here also we have a square, so we have this inequality. Well, so we have an estimate we looked for. This means somehow this T phi may be interpreted as a bounded linear functional on this space A of gamma supplied with a uniform norm. Yes? We still don't know that whether there is a uniqueness theorem for Fourier transforms, that is, whether the fact that this function is equal to 0 implies that f itself is equal to 0. So it seems to be that there may be some ambiguity in this transfer of T to this space, but in fact not, because this inequality shows that even if there is no uniqueness theorem, this thing depends only on the Fourier transform of f. So if this is 0, then in any case T phi of f is 0. So no ambiguous, no ambiguity in the definition. That is, in fact, this is a functional on this space with this norm, and this space is dense in the space C0 of gamma of all functions that tend to 0 at infinity. Or if there is unity there, then C of gamma. Anyway. Okay, it follows that it is represented by some measure. So there is a regular Borel measure mu on gamma with norm of mu at most 1, because here our functional has norm at most 1. Well, so that this functional is represented by this measure, and it is a little bit more convenient for me to write this way. So there should be the integral of f hat with this measure, but nothing changes if I write this way. So a direct application of the Riesz theorem yields a measure which represents this without the sign minus here, but then I simply can replace this measure by another one, symmetric, so that we have this inequality, this formula. So this minus is a matter of convenience. You may put it if you want. Okay. Okay. Now let's see what this means. So f hat of minus gamma, we know what this is. So this is the integral over g of f of x. And here the integral over gamma of x d mu of gamma. And here dx. So I wrote this minus here to have this term here without bar. Okay? Without bar. Well, and this is true for every function f in L1. And I remind you that t phi of f is equal to this. So if we integrate phi with every function L1, we obtain the same as if we integrate this function with the same function L1. So this means that this is equal to this almost everywhere. So the consequence is that phi of x is equal to the integral over gamma of little gamma of x d mu of gamma for almost every x. But the two functions are continuous. So in fact, this is equality everywhere. This is continuous, this is continuous. So in fact, for every x. And after that, the last argument. We also need to know that our measure mu is non-negative. Then right now we know that this is equal everywhere. So write this formula for x equal to 0. Okay. Everything is real here, since we have these inequalities. This equalities. And this is dominated by the total variation of mu, and this is at most 1. So everything is 1, and the total variation of mu is equal to mu of gamma, and this implies that mu is non-negative. So and probability. Well, and that's all. That's all with this Bochner theorem. Okay. And we still have 10 minutes before the break.
Why this implies mu is non-negative?
Because we have one here, then we have this chain of equalities. So this is 1. This is 1. Yes? But anyway, this is dominated by the total variation of mu. Anyway.
Yes.
And this total variation is at most 1. So everything here is 1.
Okay.
So the total variation is 1 and the value on gamma is also 1. Then it must be non-negative.
Why mu gamma is less than?
Because of this inequality, by virtue of this inequality, the norm of mu is at most 1. The norm of this function is at most 1. So the norm of the representing measure is at most 1. And the norm of the representing measure is its total variation. Okay? So it is 1 on gamma, but its total variation is also 1. So how it can be that it would be
Yes.
negative somewhere, or complex valued?
Okay.
Okay. May I erase all this? So the key point here is this formula for the spectral norm in terms of spectral radius. Yes? Which is also transfinite.
What?
It is transfinite. It is by its own lemma, yes, because you use the theory of maximal ideals of commutative Banach algebras, and you should know that every ideal is contained in some maximal ideal. For this you need Zorn lemma. And also you need the fact that all maximal ideals correspond to linear multiplicative functionals to the complex numbers. And this involves the Liouville theorem, from complex analysis. Liouville theorem. Liouville. So somehow.
Liouville theorem is not required.
Sorry?
Liouville theorem is not required.
Which is not required?
Liouville.
It is required because otherwise you. So if you remember this Gelfand theory, you obtain some maximal ideal. Then you consider the quotient space, and you should know that this is the set of complex numbers. And otherwise, this will be a Banach algebra where all non-zero elements are invertible, and this is impossible unless you are in the complex numbers, and this follows from the Liouville theorem. Now, what we want to prove is the inversion formula. In general, the inversion formula is something like this. What I write here, I'm going to write here is not correct, of course, but this is something like that. f of x is equal to the integral over gamma of f hat of gamma gamma of x d gamma. Well, say f belong to, let f belong to L1 of G for the existence of this Fourier transform. So at least if we take function from here, then everything is meaningful. But in fact, in this generality, this is incorrect. You know this is incorrect, even on the real line, even on the unit circle, and so on and so on. Well, but for some functions it is correct, and when you deal with the real line, you normally use Schwarz functions to write this formula, and it is not very difficult. Well, and also there is another point why this may be incorrect. Even we have something like that. The point is that this Haar measure on gamma is not unique. It is defined uniquely up to a multiplicative constant. And of course, if you change a multiplicative constant, then this formula will be violated. So the true statement is that we may normalize the Haar measure of the dual group of gamma in such a way that we have something like that, but not for all functions. The point is to we need to indicate some sufficiently wide class of functions for which this is correct. So this is the inversion formula, and I remind you that smoothness is not available in our setting, so we cannot consider the Schwarz class as an R or Rn. So we should invent something else. Well, okay, let's denote by B of G the set of all functions f that are representable in this form. F of x is equal to the integral over gamma of x d mu of gamma for some regular Borel and finite complex measure mu on gamma. So in fact, this formula may be violated simply because this Fourier transform is not necessarily integrable over gamma y. But now we consider all integrals of this form, take all measures on gamma. This time they are not necessarily non-negative, any complex measure, and take the inverse Fourier transform of such measures. So this is B of G. Now the claim, the theorem, inversion theorem claims the following. Formula marked by star, by asterisk, is valid. For every f in L1 of G intersected with B of G. And let me denote this thing by B1 of G. So take a measure, take its inverse Fourier transform. If it has turned out that this guy is integrable over G, then we have this formula. We already know that this representative measure is unique, because we proved this form of the uniqueness theorem, that if this integral, so this integral when x runs over G determines the measure mu, and this follows from Stone-Weierstrass theorem, something like that. Stone-Weierstrass. Because simply, if you remember, we multiplied this by some function h in L1, h of x, and we integrated in x. Then we obtained that the integral over of the Fourier transform of h against mu. So suppose this integral, this thing is identical to 0, then it follows that this fact, this guy is 0 for every h in L1 of G. And these functions form a dense subset in C0 of gamma, so from this follows that mu is equal to 0. So this measure mu, which represents f, is unique, and we simply write mu equal to mu f. We simply write mu f instead of mu if we have such a relationship between them. This inversion formula tells us that under this condition, if it turns out that f is integrable, mu f is simply equal to f hat of gamma. So let me write this way, the gamma. So in particular, this theorem says that this representative measure is necessarily absolutely continuous with respect to the Hauer measure on gamma. And moreover, its density is equal to the Fourier transform of f, and this Fourier transform is integrable, and so on. Well, I forgot to tell here that is valid. Let's add here, if gamma is normalized appropriately. So we need also normalize this gamma so that this be true. Okay.